I worked in the public affairs office for 30 years. I came in 1977 as an Army intern, and this was my permanent duty location, and I served 30 years, retired in 2007. Now, working in public affairs in this place where all this stuff is going on, you get exposed to lots of questions. I had to do tours, I had to answer news media questions, etc. And I didn't know anything when I got here. So I had to find out this information. I had to find out how the missile range works. I had to find out the history of the place, because there's a lot of cool history here, like the V2s, like the first atomic bomb explosion, like the Indians that once lived here, etc., etc. So for a long time, I would collect this information so I could answer questions. And towards the end of my career, people started to say, you know, you ought to write a book about that. And so after I retired, I did that, and it turned into Pocket Full of Rockets. Today we're sitting in the V2 building at the museum on the main post at White Sands Missile Range. The building houses this V2 rocket, which was captured at the end of the Second World War. The United States went into Germany to bring back as much V2 material as they could, because this technology that the Germans had developed as a weapon was way beyond anything else that the United States had. And so enough material was brought back by boat and then by train to Las Cruces, where 150 train cars were parked and then unloaded and brought to the missile range. All this material, fins, bodies, motors, etc., were stored here, and then General Electric had the contract to assemble V2 rockets and fire them here at White Sands. That program started in 1946 then, with the first firings. And the Army had the foresight to realize that they could learn a lot in addition to using them as weapons, as scientific vehicles, or put payloads in them. Up front here, we've got an area where the Germans had a 2,000-pound payload, or warhead. The scientists thought, well, we could put payloads in there. And so we sent up instrumentation here at White Sands to collect air samples, to see the composition of the atmosphere at the upper levels, to measure radiation levels at the upper levels, to take temperatures, measure the winds at the upper levels, all those things that we didn't know after the war. We'd never gotten that high. And so the missile range has always prided itself as being the birthplace of America's space activities because of these V2s being launched here at White Sands. Something like over 64, 65 of them were actually fired here at White Sands. So the missile range was established to test this new technology, and they knew they needed a big space. So this used to be a bombing range during World War II. They simply took that property, which had been leased from ranchers and miners in the area, and turned it into a missile range. And the basic real estate is 40 miles wide and 100 miles long, north to south. That doesn't actually reach 4,000 square miles, though, of military property, because White Sands National Monument sits in the middle of that, and the San Andres Wildlife Refuge is also in that property. So you subtract those out and you get about 3,200 square miles. They also have then properties on the north and west sides where they contract with the ranchers to evacuate them during 12-hour periods. And so during those periods, those 12-hour periods, the missile range is about the size of the state of Connecticut without any people out there. Consider Connecticut, what, 3.5, 4 million people. So it's a sizable chunk of property in which you can get people out of the way in case big heavy things fall out of the sky. You don't want anybody injured or killed. Okay, so White Sands is the birthplace of America's space activity. It's also the birthplace of the atomic age for the United States. So Trinity Site exists because there were two bomb designs at Los Alamos. And one was a uranium-based bomb, uranium-235, and it simply shot one lump of uranium into another lump to get a critical mass, and boom, supercritical, it explodes, a nuclear explosion. And that's the bomb that was used on Hiroshima on August 6th. That was not tested until it was dropped on Hiroshima. However, that's a very slow process to get the uranium-235 separated from uranium-238. Uranium is a fairly common element. It's like tin in the crust of the earth. But to get it to fission, to do a chain reaction, you have to have U-235, which is a subproduct, and less than 1% of uranium is U-235. So that's what Oak Ridge was all about, separating U-235 from 238. Slow, laborious, atom at a time process. They also found in the Second World War that when you run a reactor, a nuclear reactor, one of the byproducts is plutonium, which, oh, by the way, is fissionable as well. You can have it go critical if you get the mass correct. And you can make it and quickly separate it in a chemical process. So that's what Hanford was about, was the reactors there were making plutonium. And they found that they couldn't use the same mechanism to get a critical mass, because the plutonium, as it gets closer together, you'd have to assemble it quicker, have higher speeds on the cannon, or change the purity of the plutonium. They couldn't do either. So they had to come up with a different way of getting a critical mass of plutonium, getting the atoms closer together so you get a chain reaction. And so they came up with implosion. An implosion simply takes a ball of plutonium, and in this case, it's the size of a youth softball, 13.5 pounds of material. It's not very big. Surrounding it by 5,000 pounds of high explosives. And the trick is to get all the high explosives, these individual lenses, to go off at the same instant and symmetrically compress that ball down to something the size of a golf ball or something. Get your critical mass, boom. And so that was unknown, and they didn't want to just drop it on Japan, hope that it worked. They wanted to do an actual test. And so the test was scheduled for 4 a.m., but thunderstorms in the area caused delays. They didn't want to wait another day because of lightning issues, and plus everything about it is exposed out in that desert air, and the rain and the humidity might cause problems. So they rescheduled just a few hours later at 5:30, an hour and a half later, and it went at 5:30 a.m., just as there was beginning a little bit of light in the east. And of course, lit up the sky. You could see the light for over 100 miles if you were looking in that direction, depending on cloud cover and stuff. Shock wave went out and broke windows in some of the surrounding communities. Lieutenant Bush, who was the camp commander and the guy in charge of security, was at South 10,000 when the explosion took place. He elected to be outside the bunker. And he was in a hunch, and he had his eyes shut, and he was looking away from the explosion. And he reports afterwards that the light was so bright that he didn't know if his eyes were shut. The light was coming through his eyelids. So he touched his eyelids to make sure they were shut. And then after the light dimmed a little bit, he stood up. Then the shock wave hit him and knocked him down. It didn't hurt him or anything, but it did knock him down. And so people responded to that, the light. They all talk about the white light. They talk about the colors in the fireball as it rises. Talk about the shock wave. People's experience of the shock wave differs depending on their location. Some it was a loud pop. Some it was more of a rumbly, thunder kind of a thing. Some were disappointed, some were amazed. So the other issue with the explosion then is the fallout. Now everybody was far enough away and in bunkers and stuff that the radiation emitted by the fireball, the explosion in the fireball, they were safe from that. The only issue then is the fallout of radioactive dust, the materials, the daughter materials created in the explosion. And so they were monitoring that. Groves and Oppenheimer had technicians and scientists out with Geiger counters and vehicles driving along, following the plume, the cloud of fallout, and trying to measure where it fell. Because, of course, the heavier dust materials are going to fall very quickly. The lighter stuff gets pushed way up, 40,000, 45,000 feet, and it just keeps going. And so they're trying to measure that and trying to put limits on where it went. And you can go online and see a diagram of that going to the northeast, up towards Vaughn and Santa Rosa, New Mexico and stuff. And so that fallout then, of course, extends because it gets up in the upper winds. Eventually it gets dispersed and spread all the way around the planet. The other thing, the at ground zero itself, there was just a small depression, a crater created by the explosion. Because the bomb was exploded on a 100-foot steel tower, they were simulating an aerial blast. They understood that to get the maximum explosive effect on the ground, you needed to explode it up in the air at like 2,000 feet, 1,800 feet. And so they couldn't get that high at Trinity site, but putting it 100 feet up gave them a simulation of that. And so because of that, that 100 feet of air below the bomb, it didn't dig a huge crater. It just smashed down the ground. And there wasn't much dirt and debris lifted up into the fireball. Some was. There was an area scrounged out near where the tower was. But that material then, and the steel tower, and the mechanism around the bomb, all gets activated in the fireball. The sand that's scrounged up gets melted into liquid, and it falls back down as rain. And some of it's particles, and some of it is liquid. And so the crater gets covered with green glass, spotty green glass. It's called trinitite, and most of the radiation at the site itself is tied up or comes from the trinitite because it was up in the fireball at one time and activated by the radiation in the fireball. Other materials, the lightweight dust and stuff, is what went downrange. I mentioned that the V2s got us into the space age. Well, this V2 became what we call a sounding rocket. And that's a vehicle that takes these instruments to a high altitude or does some kind of an experiment at a high altitude. So that kind of a program has continued nonstop since 1946 here at the missile range. It's still being accomplished today by NASA in conjunction with the Navy here at White Sands and the Army. And so sounding rockets are still sent up because it's a relatively cheap and easy way to send up a payload to a very high altitude. And now we can send a smallish rocket to an altitude of 150 to 200 miles, well above the atmosphere, so that you can look at stars at night and there's no atmospheric interference if all you need is 4 to 5 minutes of exposure to collect that data and stuff. They've done experiments with manufacturing in the upper atmosphere. Basically, when you're up there at 200 miles, that's 0G, or microgravity they call it. So you can do some processing kinds of things to see what happens when you don't have the effects of gravity. And so those kinds of tests are continuing here at White Sands. Also, the missile range was a major player in the space shuttle program. From the earliest days of dropping scaled models of the shuttle to drift down or coast down to a landing on our strip up on the old lake bed in the middle of the range, to actual space shuttle landings, only one, back in 1982 when the Columbia landed here at the end of its third space shuttle mission. The space shuttle landing strips were used during the whole program, mainly as a training facility. 90 to 95% of astronaut pilot training for the shuttle system was done at the runways up in the middle of the missile range. And they would go very high altitude approaches and glide down for possible landings on these runways. So space still plays a role here at the missile range. So initially when the White Sands was started, a lot of the buildings here on the main post were set up as temporary buildings. They said, we're going to figure this out and we'll go out of business. Didn't happen, obviously. And so the Army set about to test this new technology and also devise new missiles, new vehicles to deliver warheads, to defend against aircraft, all kinds of vehicles. The Navy was interested in this stuff as well. Initially, the Navy was interested in the research, the payloads being put up in V2s. So the Navy has been part of the missile range as a cohort, cooperator since 1946. And in fact, eventually the missile range gets set up as an Army facility run and financed by the Army, but the Army commander, which was traditionally a general, has 3 deputies, one each for the Army, Navy, and Air Force. And those guys are then responsible for sponsoring their services testing onto the missile range. So the missile range doesn't test for just the Army, doesn't test for just the Navy, also tests for the Air Force. Holloman Air Force is on the eastern boundary of the missile range. So in the early days, they launched missiles, not only from the ground, but aircraft. That testing went on at White Sands. But so the missile range does lots of things for lots of different people. Biggest contributions would be those early days in the testing of these technologies that, as I established the National Historic Landmarks, the atomic and the V2 stuff. But then also, this is the one that people don't realize, is the ability or the blueprint for test ranges as a whole for all the services on how to set them up, what instrumentation you need, how to control tests to do it safely and all those things. The missile range was the go-to place for a couple of decades in that sense. And in fact, we used to have an instrumentation directorate here that was in charge of developing new instrumentation, new radar, new optics for testing. And it wasn't just here, other services used those same instruments then at their facilities. So that was pretty important as well. My goal, again, as a public affairs guy, answering questions from the regular people, the citizens and the news media, was to tell the basic story, and in terms of enjoyable informational stories with the information there. It is not a list of the weapon systems. It is not a list of radar systems, telescopes and all that stuff. There's some of that information in there because it's necessary to tell the story about how this all works. But I wanted it to be interesting for normal people to be able to pick up, not get lost in technology and that other junk, and enjoy some of the stories with it. So when I sign my books, I usually say, enjoy the stories.